Assalamu alaikum. Welcome to our digital electronics 2 course. Our this week topic is different type of operation modes of op-amp, and that is part 3. We had already part 2 and part 1. So this is the last part of this operation modes of op-amp. First look at the content. Multiple stage gains, voltage summing, voltage subtraction, then voltage buffer, integrators, and finally the differentiator circuit. Multiple stage gains, that's mean there will be several op-amp connected in series, and the number of stages, that's mean several stages. It may be 2 stages, maybe 3 stages, maybe 4 or more than that. So we need to calculate the overall gain of total circuit, and that overall gain is the product of the individual stage gain. That's mean if we calculate individual gain, then we can calculate the overall gain by multiplication of the individual stage. So in this figure, this connection shows 3 stages because we have 3 op-amp connected in series. The first stage is connected to provide a non-inverting gain. You see that the first one is connected with a voltage source, that is in non-inverting input connected, and there is a feedback resistor and a input resistor, that is in inverting point, and the output of this op-amp is connected with the second op-amp in the input of inverting input with a resistor R2. Then this output of op-amp 2 is connected the next input of the number 3 op-amp, that is also in inverting input. So first one is non-inverting, then next two stages are inverting gain. So if we suppose the gains are A1, the first one, A2, second one, A3, third one. So total gain will be A equals to A1 into A2 into A3, multiplication of 3 gains. So the total circuit gain will be denoted by A. So where individual gain value is A1, suppose A1, it is non-inverting, so it is 1 plus Rf by R1. Next A2 is inverting, so minus Rf by R2. That's been the resistor connected with the op-amp 2. Then the number 3 is Rf minus gain is minus Rf by R3, that is R3 is connected with the third op-amp. So in this way we can calculate the individual gain, and then finally the total gain will be multiplication of all the gains. And the result is actually the overall circuit gain is the non-inverting, because we get the first one is non-inverting and later two part is invert, again invert. So to invert is the minus will be the plus, so final result is non-inverting. An example about the multiple stage gain. The question is calculate the output voltage using the previous circuit for resistor components of value Rf is given, R1 is given, R2 and R3 for an input of 80 microvolt. So we need to calculate the output voltage for a 3-stage gain, because we have total 3 input resistance R1, R2 and R3, so definitely it will have 3 stages. Feedback resistor is given Rf, and that will be used for all the 3 op-amp, and first input voltage 80 microvolt is also given. So we need to calculate the last output V0. So you know that the total gain A is equals to the multiplication of 3 individual gain, that is A1, A2, A3, and the first one is non-inverting, so 1 plus Rf by R1, the gain value. Then the gain A2 is minus Rf by R2 and A3 is minus Rf by R3, because here it is said that the previous circuit should be the reference of this example, so we are using the first one non-inverting and the second and third is inverting. So if we put this value, we'll get the overall gain value is 22.2 into 10 to the power 3. And then we need the output voltage V0, and that is A into Vi. That's mean the gain value into input voltage. So input voltage is given 80 microvolt, and the gain is we just calculated. So final output is 1.78 volt. Another example, show the connection of an LM124 quad op amp as a 3-stage amplifier with gains of plus 10, minus 18 and minus 27. Use a 270 kilo ohm feedback resistor for all the 3 circuits. What output voltage will result for an input of 150 microvolt? So we need to show a connection of a quad op amp as a 3-stage. That means you will have 3 op amp. We need to show the connection diagram to all the op amps, and also the parameter values we should note on circuit. So it has gains, individual gains, it is already given, and the feedback resistor value is also given, that is 270 for all the circuits, and the first input voltage 150 microvolt, it is also given. So now we need to calculate also the output voltage. So now we need to calculate one by one. The first one is gain is plus 20, that's when it is non-inverting output. So for non-inverting, the calculation is A1 equals to 1 plus Rf by R1, and that is the value is given plus 10. So we can calculate R1 because Rf is given, that is 270 kilo ohm. So easily calculate R1 equals to 30 kilo ohm. So that is the first input resistor of the op amp. The next for the gain of minus 18, so the second one is minus 18, that's when it is a inverting amplifier, and the gain is A2 equals to minus Rf by R2. So Rf is given, when it A2 is, we know that that is minus 18, and unknown is R2, so the R2 is Rf by 18, so that is 15 kilo ohm. And finally the third one, that gain is minus 27, that's when it is also a non-inverting amplifier. So the calculation will be A3 equals to minus Rf by R3, and that is equals to minus 27. So unknown parameter is R3. So if you put the values, we will get 10 kilo ohm. Now we can draw the circuit. First one will be non-inverting, and second, third would be inverting. We can put the RF value, that's mean all the feedback resistors and input resistors. Input voltage is also given 150 microvolt, and what will be the output voltage? So we can calculate V0 equals to A1, A2, A3 into V1. That's mean the input voltage V1, that is 150 microvolt. So finally the output voltage is 0.729 volt, and we can draw this circuit using V0 also. I can put the value here, and we must show the connection diagram with the input resistance and also the feedback resistor. Voltage summing amplifier. So another popular use of an op amp, that is summing amplifier. So in this op amp we can sum different input voltage. So one op amp, but different input voltage can be given in the input side. So that input voltage will be added to for the final output. That's been the summing output. So how this is connected? You see that in the circuit, the input resistance, 3 input resistance R1, R2, R3, and every resistance have one voltage, input voltage V1, V2 and V3. So V1 is connected with R1, V2 with R2, V3 with R3, but feedback resistor is 1, that is Rf, and finally we will get the output VO, V0 or VO. So what will be the output VO? It is basically inverting amplifier. So the rule will apply for inverting amplifier rule gain. So minus RF by R1 into input voltage. So it has three inputs. So we'll have three individual voltage input with the gain. So gain value is R1, R2, R3 is different. So we need to calculate three different times. So RF by R1 into V1. Next one is RF by R2 into V2 plus RF by R3 into V3, and it is inverting. So in total we can put the minus. So this summation will get the result of total output voltage. So in this way the op-amp can work as a summing amplifier. So example, with the summing voltage, it is calculate the output voltage for the circuit of figure. So one circuit is shown here with the connection diagrams and all the values. The inputs are V1 is equals to 50 millivolts sine 1000 T and V2 is 10 millivolts sine 3000 T. So V1 and V2 is given, and that is in AC signal. So both are AC signal. So we need to calculate with the AC signal definitely. So it has two input voltage and with a resistor. So we'll have a two-stage connection, and that is V0 equals to minus RF by R1 plus into V1, and another one is RF by R2 into V2. So if we put all the values, so you can get the output voltage V0. And you see that V1 is AC signal. So if we put 50 millivolts sine 1000 T, so finally the result will be something that will also carry the sine and 1000 T. So it will not be removed. Okay, so it will be there. So it doesn't matter. But yeah, the result is in AC in AC signal pair. Voltage subtraction amplifier. So another type of op-amp that can subtract from one voltage to another, and it can show that output to final output as the total circuit. So two signals can be subtracted from one another in a number of ways. There are several ways actually. One way is showing in this circuit, that is two op-amp stages used to provide subtraction of input signals. You can see the first one signal is V1, that is in the inverting point of the first op-amp, and second voltage is V2, that is the second input voltage of second op-amp V2. So this V1 and V2, actually these two will be subtracted from one another, and finally it will show the output in V0. So first one is V1 is connected with R1, and there is also a RF feedback resistor with the output, and second op-amp has the feedback resistor RF, also the input resistance R2 with the V2, and between first op-amp and second op-amp there is another resistor, that is R3. That's why the equations is a little bit changed. You see that the output of VO is equals to minus RF by R3. So this 3 is connected with this RF by R3, and minus RF by R1 into V1 because they are inverting amplifier, and plus RF by R2 into V2. Second one is also inverting, but there are in first there is a minus. So we can conclude finally after rearranging the sentence, that is V0 minus RF by R2 into V2 minus RF by R3 into RF by R1 into V1. So this will be the final equation for voltage subtraction amplifier. An example is given for that subtraction circuit. Determine the output for the circuit of figure with components RF equals to 1 mega ohm, R1 equals to 100 kilo ohm, R2 is 50 kilo ohm, and R3 is 500 kilo ohm. So calculation will be like the previous one that was given in the circuit. So V0 equals to directly the results are given here. 1 mega ohm, that is RF, divided by 50 kilo ohm R2 into V2, minus 1 mega ohm RF divided by 500 kilo ohm, that is R3, and 1 mega ohm divided by 100 kilo ohm, that's R1 into V1. So the final result is 20 into V2 minus V1. So this output is the difference between V2 and V1 multiplied the minus 20, that is the gain factor. So if here V2 and V1 is not given, that's when the result is not given, that's why the output is showing you with the V2 and V1. But if we had some values for V1, V2, then we can put that numbers here and we can get the final output V0. Voltage buffer. So this voltage buffer circuit provides a means of isolating an input signal from a load by using some stage of voltage gain, and it should have normally unity voltage gain. You know that unity voltage gain is when RF and R1 is equals. So here actually it is given that there is no RF and R1, so no feedback resistance, no input resistance. That's why output is directly connected with inverting input, that is short circuited, and that's why V0 is equals to V1. V1 is connected, input voltage is connected with the non-inverting side, so output V0 is dependent only directly V1, so output must be V0 equals to V1. So this op amp is to provide the buffer amplifier operation, and here no phase or polarity inversion is happened. That's why it's a unity voltage gain and acting as an ideal circuit. Another type of voltage buffer circuit is here. This one, two op amp, one input voltage is connected with both of the op amp, and we have two output voltage V01 and V02, and V1 is connected in both of the circuits inverting non-inverting terminals, and we do not have any feedback resistance RF and R1. So in this way one voltage is separated into two without affecting each one, okay, without affecting with each other. Example, show the connection of a 741 op amp as a unity gain circuit. So we need to show only the connections as a unity gain circuit. So for unity gain circuit, we know that we need to show the RF and R1 must be 0. There will be no RF R1. That's why the circuit is shown here. Output, but between output and input, that's mean from point 4 to 10, there is no feedback resistor connected, and V1 is connected input voltage with the non-inverting terminal, that is in 5, and output is taken from V0, and there will be a supply voltage, that is plus VCC and minus VCC at 11 and 6. That is the 741 as a unity gain circuit. Integrator circuit, integrator op amp. So you see, with the name implies, the op amp integrator is an operation amplifier that performs the mathematical operation of integration, and we know what is integration. So that integration mathematical operation can be performed through this integrator circuit. So this is the connection diagram. So there is a capacitor instead of a resistor, the feedback resistor. You see that the capacitor is connected between the output and input, and this capacitor, you know that it can store charge and discharge the charges in some over time. So that output actually depended on the input voltage over time, not only the input voltage, also with the time. That's meaning at different time the output voltage can vary. That is the main theme of integrator circuit. So in another words, the magnitude of the output signal is determined by the length of time a voltage is present at its input. The current through the feedback loop charges or discharges the capacitor. So the output voltage is can be calculated through minus 1 by R input into C integrator of 0 to 2t V input dt, and finally it can be also written as minus integration of 0 to t V input dt by R in into C. This, you know that R input and C capacitor, they are constant term, they are not varied with the time, so only a time dependent time variable is V, voltage, input voltage, that will only vary through the time. So we need to integrate only this portion, V input. Differentiator circuit. So another circuit of op-amp, different type of op-amp. So this is the reverse process of integration, so it can do the mathematical operation of differentiator. So the output voltage is the differential of the input voltage. This is very useful for finding the rate at which a signal varies over time. You see the connection diagram, the capacitor is now in the input signal and it has the RF, the feedback resistor RF here between the output and input, but the capacitor in input circuit. That is the difference between an integrator circuit and the differentiator circuit, the placement of the capacitor. So the differentiator circuit equation is V out equals to minus RF into C and differentiator of V input divided by dt. So this is the equation to find out the output voltage of a differentiator circuit. So here it is also RF and C is constant, they are not derivated by time, so only the derivated variable is input voltage V in. Self-directed learning of this week is, the question is there any similarities between differentiator and differential circuit? So you need to study that is this two circuits same or difference? There are difference between them. In this week we have forum and a quiz, so please participate all the activities in due time. So that's all for this week. Thank you.